Okay, so we have Marguerite Laborde here with us today. She's going to talk to us about Nielsen and Chuang, sections 1.2 and 1.3, which are essentially an introduction to quantum computing. So take it away, Marguerite.
All right. Let me share screens. Okay, so I figured we'll just do this like lecture style notes, primarily because I had another presentation this week, and so this is what y'all get. But so essentially, this whole first chapter is just an introduction to quantum computing, and primarily sections 1.2 and 1.3 are just an overview of what to expect. So really quickly, some preliminaries that we are like skipping over from your preface, and a little bit of the motivation, but we don't really care about motivation. We're already motivated to be here. So for our group, we're a mix of like math, physics, and comp sci. So the physics people are going to be really comfortable, I think. A lot of the things here maybe won't surprise you if you've had a quantum class before. If you're math, everything is linear algebra, so that's pretty convenient, but you should just note whenever there's a log, it's base 2 because we're doing computer science, kind of, sort of, not really. And we're always going to try and work in a binary register unless otherwise stated. That's your computational basis. And we require, whenever you're taking an action in a quantum circuit, that they're always unitary matrices. This is just like a quick overview. Things we're going to get into much more in depthly. Also, comp sci people, there's going to be a bit of a learning curve on that side because there's things that are super easy to do in regular computer science that are not nearly as simple to do in quantum computing, but then also vice versa. The biggest thing I think that will be weird is if you've never seen bracket notation. So bracket notation, let me just make sure I have a pen on. Let's do this one. So bracket notation has a bra with something here and a ket with something here, and it's used to express inner products. And TLDR, what you need to know is that a ket is a column vector, and when we're working in this case, it's a 2 by 1 like that, and a bra is a row vector. So it's that's an expectation value. That's incorrect. It's like this. And basically, the way you can read this, if you're more familiar with comp sci, is you start counting in binary. So this will be 0 and this will be 1. Likewise, 0, 1 here. And that's
shouldn't it be a star?
Yeah, I mean, like if you're taking this to be equal to the actual complement of this guy, or Hermitian conjugate of that guy. I'm just trying to like write it out. If you've never seen bracket notation before and you don't know what this squiggle thing is, but yeah, in general, if these two are the same symbol, then this is the Hermitian conjugate of this guy. The other thing that's different from comp sci is that you have to have every gate be reversible. So anything you do, you should be able to undo. And the easy way to spot that is just everything must have the same number of inputs as it does outputs. So, and the last thing, which we're going to get into in more detail, is no fan-outs. There are absolutely no fan-outs. Asterisk. Technically, there are fan-outs, but they don't behave the way they do in regular comp sci. Also, I included the notation from the beginning of Nielsen and Chuang because I can print this to PDF. And if you want to pull up a much smaller PDF that has all that stuff here, here you go. I think it's a very useful reference. All right. All that being said, quantum bits. So when you're doing classical computations, we're familiar with the terminology of a bit, right? Old school video game enthusiasts often talk about like 8-bit versus 64-bit consoles, things like that, which were used as slang for computational power. Sorry, I just noticed the chat was going off. So in classical computing, you can think of a bit as being like a light switch. So on or off, 0 or 1, kind of like in the picture to the left of the screen. But what does that physically mean whenever you're talking about building a circuit? Well, physically, a bit is actually given by current or voltage in a wire. So you might have some schematic drawn out like this, where you have your battery giving you some voltage supply, you have your circuit that does some stuff, and somewhere along the way, whenever you're doing your calculation, you measure the voltage somewhere. And you have some set voltage. I think 0.5 volt is normally the activation voltage. I think I've heard 1 volt or 5 volts before too, but it's pretty low, but you have some voltage threshold, and you say if whatever voltage you're measuring is greater than that, then that's a 1, it's on. But if it's less than that, it's 0, it's off, right? So that's physically how you're doing your math whenever you're going back and forth between your computational bits and your physical setup. And then all of your computations are done physically by like adding, splitting, or otherwise manipulating this voltage. So whenever you're talking about your actual gates, it's really just transistors and things in the wire. And everything that you're doing mathematically is represented by just electronics dealing with these voltages to add up. However, for information purposes, it's easier to consider the 1s and the 0s, that your binary code, to describe your actions of your algorithms and circuits, because, you know, maybe if you're doing computer science, you don't necessarily care how transistors work, you care about how they add your voltages together to do your computations. So yeah, you don't care about how you're adding 5 plus 2 in terms of your actual physical circuit. You just care about like, oh, well, I have some binary voltage I can express as 5, and I have another one I can express as 2, and then you add them together and you get 7 in binary. And that's how you do all of your computations classically, and you know that should be a little bit more familiar if you're familiar with regular comp sci. So what changes when you move to a quantum bit, which, I mean, this picture up here kind of describes it a little bit, whereas this one looks like an on and an off switch. Now you have some strange sphere to consider. So this is the Schrodinger's cat style change in bits that people often reference. I don't quite like the Schrodinger's cat analogy here because it's horribly misinterpreted most of the time. But you can kind of think of switching between a classical bit and a qubit as being like, before you could live only on the north and south pole of the globe, but now you can live anywhere on the globe. And spoiler alert, also kind of inside of it. But you can still only answer that you live on the north or south pole. So you gain a lot more space that you're allowed to live in here, while still technically only ever giving the same answers at the end. Your travels are more complicated. So what does that look like mathematically? Well, your qubit now is no longer like 0, 1, something clear and precise like it was in the case of your voltage determined classical bits. You have some qubit, which we state in terms of a ket. It's typical to write a psi inside of your ket. If you've never seen bracket notation before, whatever you write inside of a ket technically doesn't matter. You could make a smiley face ket, and this is perfectly valid as long as you define what it means and you're consistent about it. So maybe smiley face is 1 square root of 2. Right, that's perfectly fine. What's inside of a ket doesn't matter. What matters is that you're consistent about it. Typically, we set some random qubit to be equal to some psi, or phi is also choice. And then in our computational basis, to make it look more like typical computer science, we have some basis states 0 and 1, which are given by these kets. And so your typical ket 0 corresponds to this column vector, and your typical ket 1 corresponds to this column vector. Right, and again, if you like read through each of the entries by counting in binary, this is 0, this is 1, right? That kind of makes sense a little bit. And you can do some quick algebra and find out the inner product between 0 and 1, which you write like this, is equal to this guy. And this is 0, okay? But meanwhile, if you take 0, 0 or 1, 1, you get back 1, okay? That's the worst one I've ever written in my life. Okay, so this is an orthonormal basis, the preferred basis to work in for most people who do quantum computing, just because it makes your math easy. So you've broken this up into components, like equivalent to if you're dealing with a normal vector that has an x direction and a y direction, they're orthogonal, so you can treat them separately. So this is one of your basis states, and this is the other. What are alpha and beta? Well, first, I state that alpha and beta are complex numbers, and we have the requirement that the magnitude of alpha squared plus the magnitude of beta squared must equal 1. This is our normalization condition. And we say that alpha squared and beta squared are the probability to get 0 or 1 respectively. So we might refer to alpha and beta individually as probability amplitudes, and then you square them to get the probability of that particular outcome. So if I'm doing some sort of quantum computation and I have a qubit that looks like psi here, and I want to measure to see if it's 0 or 1, I'm not guaranteed anymore for any arbitrary qubit to always get the same 0 or always get the same 1. And now it's a probabilistic thing. So I wanted to have a quick aside here. There's a book which I think is an interesting read, maybe not the most entry-level friendly book on the topic, but Scott Aronson wrote Quantum Computing Since Democritus, which does take you through a lot of the computing quantum information thought process that went on behind a lot of the current science that kind of underlies it all. And in particular in chapter 9, when he switches to talk about how quantum computing is formulated compared to other forms of computing, he talks about why we do this, why we have these probability amplitudes, why they're complex, which might seem strange to you because, you know, complex numbers are imaginary and this is supposed to be a physical thing, and why you square them. Physicists will say we do this because this is what works. If you do experiments, nature behaves like these probabilistic amplitudes, and it works out better when they're complex. Our mathematicians might say that, well, you have to have A and B be complex numbers because the complex numbers are algebraically closed, and so they can solve all of their own equations without going to a higher space. The simplest part of the arguments, though, if you've never seen why we're doing this, beyond just experiment says that this is how nature works, is essentially occasionally you're going to get something where you want to solve a problem that looks like x to the n plus y to the n is equal to z to the n. And if you're trying to solve this problem, n has better equal 1 or 2. And if it's 1, that's classical probability. And we know that classical probability doesn't work for quantum computing, for quantum mechanics in general. So we better pick 2. So we have to be squaring things. And then moreover, if we're going to solve all of the problems without going to higher dimension, so think of the square root problem, right? If you have a square root of a negative number, you can't, this is not contained in the reals. Therefore, you know, that there's an inherent problem there. We want to be able to solve all of our problems, so they better be complex. That is literally why complex numbers were invented, discovered, depending on what side of the debate you're on there. But, all right, so that was just a quick aside. Why we have that strange structure for probabilities in our qubits. But how does that actually work? You know, if you haven't seen like the probability amplitude description of quantum mechanics before, let's go through an example of how that would actually be interpreted whenever you go to measure something. So the pop science explanation is that a qubit is like a mix of 0 and 1. You know, classically you have zeros and you have ones, but then quantum mechanically you can be both at the same time, and that's a little bit disingenuous. It looks like something in between, more like less so of being both, more so of something that's just a mixture that's exists somewhere in between on a spectrum. So we can take the example of the plus state, which is defined as an equal superposition of 0 and 1. So they have the same weight, that makes them equal. And then we're adding 0 and 1, so we call it plus. But again, you can define this to be any sort of ket that you want. When you go to measure this, you can figure out your probability to get 0 by just taking the amplitude of 0 and squaring it. That's 1/2. Same thing with 1, you get back 1/2. So 50% of the time, you're going to get 0 if you measure this sort of qubit. 50% of the time, you get 1. So this kind of looks like a quantum coin flip. So why is this any different from a classical coin, you might ask? You know, why the weird square root instead of just, you know, flipping a quarter? What possible benefit can this give us? Or at least how is it different from something that might be more convenient to do? First off is that this is truly random. So if you're Newton and someone tells you they're flipping a coin, you say, well, if you explain to me like all the air currents in the room and the momentum you had when you flipped the coin, all of these things, there are a bunch of variables that go into that coin flip. And if I know all of them, then I can predict whether it'll be heads or tails. And so what looked like it was random is actually just a byproduct of physics that I don't know, but is perfectly knowable. Whenever you go to quantum mechanics, however, this is not true. There is a level of fundamental unknowability to your outcome. The interpretations of this differ greatly. Whether you're saying like, well, actually the coin itself doesn't know what it's going to pop out to be until the end and the wave function collapses, or maybe you do multiverse theory and you're like, one universe it comes up as 0 and another universe it comes up as 1, and if you take all of the multiverses it gives you a 50-50 difference. All of those interpretations, the book doesn't go into them, and to a large degree they kind of don't matter because the end result is still the same and we can't differentiate between these interpretations. And that end result is, this is truly random. You don't know what the outcome will be until you measure, and there's nothing, at least not locally, that is hidden in these coin flips that you can use to determine your outcome. Practically, what difference does that make? Well, without getting too much into particulars, it can make a lot, and you can see this in a sort of pachinko or random walk scenario, which you can feel free to ask me about if you're not done listening to me ramble at the end of this talk. But so you can talk about that, or also there's an infamous case where Monte Carlo sims predicted that the universe repeats, which spoiler alert, it doesn't, as far as we're aware. So there are instances where you would really want true randomness that classical coins cannot give you, but a quantum mechanical coin that looks like this superposition might actually be able to do that. Okay, so going back to a general qubit, I tend to write them in the form I did before, where you just have some complex alpha, complex beta, like that. But there's a more general, more precise way to write a general qubit, which is given here, where you have two variables that determine it. They're both angles. A quick count might make some of you say there are 3 on this first line. However, whenever you have a global phase like this, we say that doesn't matter. It doesn't change anything. It's unmeasurable. We only care about differences in angles. And because this is the global phase, we get rid of it. It's not necessary. But then you can further elucidate the state of your qubit by saying, well, okay, my 0 is the cosine of half of some angle, and my 1 is the sine of that same angle, plus maybe some phase shift, some relative phase shift, which is physical and measurable. Whenever you're going through doing quantum mechanics, not just quantum computing, anytime you see a global phase factor here, or you see a phase factor maybe like written here, it's like e to the 2 phi, like that, and one here, you're always going to try to get rid of it. Just general rule of thumb is that you shouldn't have every one of your basis states with a phase, because that doesn't matter. You can't measure a phase in and of itself. So we only care about a relative phase, which is encapsulated in that second term. And then that's where you get this second line from. We just get rid of our general phase. Now, why would you want to write it this way instead of just saying, oh, there's just some complex number there? Why do we care about the relative phase between our 0 and 1? Well, like I was specifying before, 0 and 1 can be seen as like your basis vectors sitting in some sort of vector space, or in this case, the block sphere. And they tell you relatively where your vector sits in this spherical space. So we say a qubit lives on the block sphere, which is a fancy sphere insofar as if you do a full rotation around it, you haven't gone 2 pi, you've gone 4 pi. Okay, so that's an interesting facet of this. If you do a rotation of 2 pi, you don't get back to the same spot you were. You're at like the antipodal point, which is pictured here, 0 and 1 being orthogonal, and they're at 2 pi away from each other, right here. So, and this sort of construct where you have like a cosine and a sine of an angle and then a relative phase allows you to specify your state as just being some point on the block sphere. This can be useful if you're looking at your gates as rotations. So instead of just like looking at a circuit diagram, maybe it would be easier for you to think of a vector or like an arrow that you're then rotating around your space to get to your new coordinates. And in that case, the block sphere is a visualization that I think a lot of people really like, and it makes things make a little bit more sense. Okay, problem with the block sphere is that it's only really good for picturing a single qubit. So how do you move to a higher order style of qubits? How do you get more? Oh, just to like let y'all know, I don't get the immediate notifications for the chat. So if y'all can just like unmute and chime in, that would be preferable. Yeah, okay, so the reason you can get rid of the global phase is you can consider the global phase rotating your whole block sphere, kind of. You can't differentiate between the sphere rotating all together versus, you know, your vector moving with respect to the axes. That's a lot more physical. Your whole system rotating doesn't actually like show you anything measurable in physics. And okay, and then there was another question. Sorry, it's very hard for me to scroll with this little pin. Yeah, okay, so the pi gate, the poly Y gate, so they're still rotations, and they don't take you as far around as you would expect from a typical sphere though. So if you have a 90-degree rotation or a pi over 2 rotation, it actually looks more like a 45 whenever you picture it in this scenario. Same thing, because you know these two are completely orthogonal to each other. You tend to think of that as pi over 2, but this looks like pi, right? So I mean, part of the reason, full disclosure, I don't really like the block sphere is because it makes the mental picture of the rotations look a little bit weird. And I prefer to just deal with pure linear algebra, but more graphically minded people get more interpretation out of this picture. In particular, the full rotation being 4 pi around is reflected in your math here. So, you know, if you rotate by an angle pi over 2, well, that's your theta here, and then you take another half of that, and so you've gotten pi over 4, and that's just how your geometry ends up developing. If that answers your question. Yeah, 0 does not equal -1. Okay. All right, so, all right, like I was saying, block sphere can be useful for visualizing the action on a single qubit, but what if you have more than one qubit? They're created through something called a tensor product. So say I have 2 kets, psi and phi, representative of qubits each, where alpha, beta, delta, and epsilon are all complex numbers. And maybe for our convenience, we'll even let epsilon be less than 0 if you want to be clever about it. So the way we write the state on these multiple qubits is we write them this way, which is equal to this, which is equal to this. Number one reason people just tend to write them in one ket is because it makes your notation a little bit cleaner, but it's equivalent to taking this tensor product, which if you've never seen a tensor product before, it's just a matrix product wherein you take all of the elements of one. So say you have a vector here and another one, and you multiply it by the full vector, the full second vector in your second slot. So it looks like A times CD, B times CD, and then your full output will give you AC, AD, BC, BD, right? Very quick tensor product rundown. So keep in mind that these kets are all representative of vectors. So when we do this sort of notation, we're saying, hey, we're doing this sort of tensor product here. And sometimes it can be useful too to say like, oh, this is qubit A and this is qubit B. So sometimes we'll use this notation whenever we have like a gate acting on only one qubit versus the whole system, to keep track. But typically speaking, people just want to write them in one ket, and that's perfectly fine. But whenever you go to these higher kets, now you have more basis states. So instead of just having 1 and 0, you have your double 0, your 0, 1, your 1, 0, and your 1, 1. And pro tip, whenever you're writing out the actions of your circuits, it can really help to always write them in counting order in binary, 0, 0, 0, 1, 1, 0. And that's because whenever you go to your algebraic system, that's what the order of these correspond to. So these are the states that they correspond to when you write them in bracket form. And so I just think it makes it easier if you always write them in order when you're doing computation. I don't always follow my own advice, but I do think it makes it a little bit easier. Okay, so you have this, you have multiple qubits now that you're writing all in one ket. What happens if you measure one? Well, from our coin flip before, if you have just one superposition qubit and you do a measure on it, it'll give you 0 or 1. If you measure that same qubit again immediately, you're going to get the same answer. It doesn't have time for the wave function to evolve in physics terms. Or you might think you've already measured it, you've collapsed Schrodinger's cat into alive or dead. You can't restore that superposition you had before. But now what if you have multiple systems? Instead of, I measured once and I get a 0, and then I go to measure again on something I've already measured, I have that 100% certainty. Is there anything extra that comes in when I have more than one qubit? And there's a few things. So you can measure on one qubit and not necessarily disturb the second. That is not always true, but in principle you could. And when you do that, say we have our multi-qubit psi and phi, and we measure on psi, and we got the result 0, for psi. Now psi is stuck in the 0 state. What does that mean for your resultant state afterward? So your post measurement state is now psi has gone to your 0 ket. It is stuck there. Just like after the coin flip, it's done. Schrodinger's cat is dead. Then you still write it as a tensor product with your undisturbed state before. So whereas you could have written your total state afterwards like this, in this sort of long form basis state expansion, now you only have the states wherein the first qubit is 0 because you've measured that. It's stuck in that state altogether.
Marguerite,
Yeah.
Alex had a question in the chat. He can't talk
Okay.
right now out loud.
Okay. Okay, so he's asking, how long does it take for the waveform to evolve? Is there some norm refractory period for a waveform? So that depends on what type of waveform you're looking at, like a characteristic time length. And that really depends on the system you're looking at. Generally speaking, we say if you take a measurement well within the time specified by the wave-like behavior of the particle you're considering, then you're going to get back to the same state. What does that actually mean, though, if you've never seen like quantum physics before? Well, the time evolution of a quantum state goes like e to the goes like this, where this guy is your Hadamard. You can kind of consider it like your energy scale. So whatever energy state you're in is gonna evolve at that time scale. So you can think of things that have higher energy evolve faster than things that are at lower energy. If that makes sense. This is like trying to very hand wavy explain like all of modern physics and solving the Schrodinger equation, but just know that different states have different energy levels. So this thing looks like a relative phase. So you might have something that looks like that. And you need your time scale to be long enough such that the total energy associated with this state is large enough to make this number significantly different from 0, if that makes sense. So this state has some energy, and you want the total resultant time scale to be such that something that looks like that is significantly greater than 0. And that kind of gives you a measure. All of that is like way more in depth than you're really expected to get from your introductory chapter. But that's generally speaking. Also, we're doing quantum control, where we're trying to keep our qubits in the states that we put them in. So for quantum computing purposes, you've measured it. You're trying to keep it in that collapsed state. You don't want it to re-evolve. Also, until you start doing unitaries to it. Letting your state decohere can also be represented by a unitary, but generally speaking, we don't want to do that. We want to maintain the states we're in. So good question. A lot more into it. Maybe we can talk about it afterwards if it's not clear yet. Okay, so measurement on multiple qubits. So you've measured one qubit, you're in your 0 state, and you want to keep it in the 0 state. So what that's done is it's affected the total state of your system, so that you only get to keep these states here. I don't know if y'all can see the little dot from the pen, but here that correspond to your first qubit being 0. And so we do that here. However, we need to preserve our probabilities. We need to make sure that whenever we measure, we have 100% probability of measuring something. Okay, and the way you reflect that in the math is you renormalize it, same way you do any vector. So that's what's going on here. We're just renormalizing it. And then you can very quickly see, well, you know, the alpha pops out. And so you get something that looks like this guy, which then looks like you just took your initial state and did this with it, right? Because you assume phi is also normalized. Okay, so that's what a post-measurement state would look like. Again, very quickly, this whole chapter, we're moving through a lot of concepts really quickly. So don't feel bad if it feels like I'm just blowing through things, because even I feel like, all right, this is a lot really fast. So an interesting 2-qubit state that we're going to mention now and then come back to at the very end is the Bell states, or the EPR pairs. So EPR pairs are, I always forget the middle guy's name. It's Einstein, Polinsky, yeah, and Rosen. Okay, yeah. We know Einstein's name. So EPR pairs are named after their paper, where they basically all got together and started complaining about how quantum physics didn't make any sense, and it was a big, stupid, dumb theory, and everybody should call them out for not being complete. And there's basically a list of things that they didn't like about it, like non-locality and non-reality, things like that. And I think this is actually Einstein's most cited paper by people who are citing it to say, hey, look at this thing that quantum physics did that would piss off EPR. It exhibits one of those things that they didn't like, non-locality and unreality being the really big ones. So these EPR pairs, or Bell states, are so called because they're your go-to states to exhibit one of those weird factors of quantum mechanics. So if you look at the state here, you'll see that your first qubit always matches the state of your second qubit. So whatever you measure on one, you're guaranteed to find the other qubit in that state. So these qubits are perfectly correlated. And in fact, they show stronger physical correlations than anything in classical physics allows for. So you can build these states, they exist, and there's nothing in nature classically that exhibits a higher level of correlation than these states. And we call these states entangled. I used to know the origin of that, and it had something to do with enfolding, but I don't anymore. And basically you can just say, an entangled state is a state that you cannot write separately. So before, I was writing something that looked like this as a tensor product, and you can try your hardest, but no matter what you do, you cannot write this state in that form. You can't undo the tensor product because it doesn't factor. When you can write it this way, and it's easily viewable, that's called a separable state, and sometimes we refer to those as classical states, which, you know, maybe a little bit of a misnomer there, but we refer to them as being classical versus this is an entangled state. You cannot write it in a tensor product form. You cannot separate them. Therefore, they are entangled with each other, like they were tied in knots. They cannot be undone. So this is one of the big things from quantum physics that actually comes into quantum computing pretty often. So Eliza asked, are separable states also known as product states?
I want to say the answer is yes.
Yeah, so I feel like she's testing me on my vocab right now. So I want to say yes, because the product, this is a product, right? This is a tensor product. I feel like some people, like for example, Professor Mark Wilde, who Eliza and I work with, might be able to point out some subtle difference between the two, but product states and separable states are not entangled. They are both not entangled. So entangled states are not those, and so I'm going to go with yes for our intents and purposes. I feel like there's a subtle difference between them that I am not remembering right now, but that could just be me not remembering. Okay, cool. So, all right, last thing to mention about our qubits is the space they occupy. So again, if you're used to classical computing and classical bits, your computational power, the space you can occupy goes by powers of 2, right? So you have 1 bit, you can write 2 numbers. You can write, 0 and 1. And then if you have 2 bits, well, you can go all the way up to 4, so on and so forth. For an n-qubit system, it scales much faster. You get a 2 to the n Hilbert space. So whereas this is giving you discrete numbers also, so these are discrete, and this is classical. Your Hilbert space is not discrete. This is continuous. So you're living in a much higher parameter space, or as the quote at the beginning of the chapter says, Hilbert space is big. It's a pretty big space. So it goes as 2 to the n, and what that essentially means is you very quickly get too large for classical computers to handle. There's a bit of a debate in the fields of computing, classical and quantum alike, about whether or not classical computers are really good enough. There's something called the extended Church-Turing thesis that says that any reasonable calculation that can be done efficiently can be done efficiently on a Turing machine, aka a classical computer. This is, you might have noticed, a very wishy-washy theorem, like what is reasonable, what is efficient. And so classical computer proponents, they say, well, you can't get anything more from a quantum computer than we can get from our Turing machines. And this is I feel like the biggest argument against that, because even if you can't do any algorithms faster, your space that you're exploring is so much bigger, because you're able to simulate your quantum system better. If you get n equal to 50, so you have 50 qubits, the book points out that's more than the number of atoms in the universe. There's absolutely no way you'd be able to simulate the action of 50 qubits on a classical computer. You would run out of atoms. So, right there and then you get that there's an advantage to a quantum computer insofar as it can live in a quantum Hilbert space. It can just explore the space without, using up the whole universe in your CPU. So, that's your go-to advantage. That's why a lot of people are really interested in quantum simulations also, is because it's just naturally easier to just work with quantum states. All right, so that's all about the quantum bits. 1.3 deals with the actual computation. So computation comes down to logic gates and wires. For convenience, most people, always just assume that your input states to whatever circuit you're dealing with are zeros. And you can do this without loss of generality, because you can create like a 1 or a plus state with a gate. So you can, without loss of generality, always consider your inputs to be your 0 states or your 0 kets, and then you manipulate them with logic gates and you move them with wires. That's what it comes down to when you're looking at a quantum circuit. So wires just carry your information. Classically, that's bits. Quantum mechanically, that's qubits. You just put quantum in front of it and it makes it better. And then your gates, your logic gates, perform operations to manipulate the information. So you don't let your wires change your information, typically. You do that in logic gates. So even if your wires were, physically changing things, you would pretend like they didn't, and you would just insert a gate there in your theoretical circuit. That's how we treat that. So classically, there are a lot of gates that you can do. And I wanted a little bit of audience participation. So one of these gates you can use for quantum computing, as is.
Pick me.
No, you're cheating. Anyone? The NOT gate. Yes. Thank you, Eliza. So you can use the NOT gate because, and you can immediately check this, it's super easy. Number of inputs and number of outputs match. You think Eliza is cheating? Yeah, I think it is cheating that she's studied quantum computing since she was in high school. That is very unfair for everyone else. All you overachievers. So we require that everything be reversible in quantum computing. Another way to say this is that we require everything to be linear. Why do we require things to be linear? Because nature is linear. And so if it behaved non-linearly, we would be in trouble because we wouldn't be simulating nature, which physicists are very concerned about. So yeah, the correct answer is A, the NOT gate. We can manipulate one of these gates. I don't know actually if I need it here. No, it's not in here. There's another gate that we can manipulate and then use for quantum computing, but as is, we only use the NOT gate, which is their only single bit gate. So when you make a circuit, classically, you just draw a bunch of wires and you put a bunch of logic gates, and this is how you physically, visually represent your math on your system. Same thing with quantum circuits, only now you do quantum logic gates, manipulating quantum bits. Again, you just toss the word quantum in there and now it's better. Fun fact, all of these circuit diagrams, both classical and quantum mechanical, are technically a type of tensor network, if you've ever heard of those before. I gave like a rundown at a group meeting for Mark Willie on this one time. Put it up on YouTube, and one person thought it was very useful. I have no idea how they found it, but if you want a quick rundown on tensor networks, you can probably Google that and hear me ramble about that as well. But essentially, a tensor network and a circuit diagram are just a way to visually do math without necessarily writing out all of your states and doing all of your linear algebra, because sometimes we don't feel like matrix multiplication. Okay. I mentioned this before, but it's your real big enforcing rule whenever you're doing quantum computation, that you must preserve probability. What does that mean? It means you don't allow yourself to have over 100% probability of measuring things, and you don't let yourself have under 100%. It has to be exactly 1. So you can think of this as saying is like, there's no chance that you measure and don't get a result. And there's no chance you perform one measurement and get more than one result. You always have one result. And mathematically, the way you represent this is that you just enforce the condition that for whatever your total state is, whenever you sum up all of your coefficients like so, and like this generalizes, and the book mentions that, this must always be true, always. You enforce that condition. How do you actually do that? Well, this is where the unitary matrices come in. So a unitary matrix, you can define it to be some matrix U such that the magnitude of your determinant is equal to 1. That's one way. Equivalently, and this is perhaps the more insightful mathematical way to look at it, you can say that U must be such that the Hermitian conjugate of U, which is just U dagger, so this is Hermitian conjugate, otherwise known as the conjugate transpose, that times U is equal to U times the Hermitian conjugate is equal to your identity. I would call that like self-adjoint, but I think math people get mad when we throw around words like adjoint and maybe don't know what they mean. Zach?
So yeah, so self-adjoint is so the dagger here, the Hermitian conjugate, is what a mathematician would call an adjoint. And when U dagger is equal to U, we call it self-adjoint when you're in a finite dimensional vector space. But there are some things to resolve about domains when you move to an infinite dimensional vector space. So that's the only thing.
Yeah, okay. I knew I would be using that term wrong, but yeah. So we say that this is the interesting property for a unitary matrix, and it means it preserves the inner product, or it preserves probability. Okay, so if I didn't explain kets to vectors, now is the time. I kind of already did, so that was just a note from me to me. So mathematically, if you have some n-qubit state, it's a column vector. And what the action of doing multiple qubits is, so I said like a multiple qubit state does like this, and I showed what a tensor product was. What this actually means is that the dimensions go like, so your dimension of this thing goes like the number of rows here and the number of rows here multiplied together. So if this has n rows and this has m, it goes like n times m by 1. What does that mean? Well, essentially you end up, this is 2, this is 2. You always get 2 to the n by 1 column vectors out whenever you have n qubits. So it gets very big very fast, which is one of the reasons why we stop writing out our column vectors and we go to our ket notation, because it can be very inconvenient to do that. So you have some arbitrary n-qubit state. It's a column vector with 2 to the n entries, and then that means for a 1-qubit state you have a 2 by 1 vector, and this is the computational basis that I mentioned before. This is both convenient and notation for the field, and it's pretty standard. So this is always the case. This is not the only choice for basis, though. You could, in theory, do some other basis, which we go through the plus minus basis a little bit later. But you try to always use an orthonormal basis because it makes your life easier. Are you required to use an orthonormal basis? No, but you try, because life is easier when math is easier. So, and again, you can write out the kets using this linear algebra. And so if you have like a single qubit state, you can write it like this, where you essentially just write your probability amplitudes in your vector that correspond to the state of interest. Now, okay, using that notation, say we want to move from one state to another, and we want to preserve this sort of dimension. Well, linear algebra tells us the way to do that is a 2 by 2 matrix that looks something like this. And then we also require you preserve probability, or the inner product for our math nerds, and that looks like this. So that says that this is determinant magnitude 1 of this matrix. All right, so all of our gates are going to look something like this, with this condition. All right, so an example is the NOT gate. That's the one we said we could use. We also call that the poly X gate. Classically, that's the only one bit gate, because your only allowed changes are from 0 to 1 or 1 to 0. Technically speaking, you also can have an identity, which is your wire, but that's pretty trivial, and so no one cares. So doing the truth table for your NOT gate, you only have 2 inputs and 2 outputs, and it has this sort of action that we see here. But now quantum mechanically, we have to put them in kets. See how that works. So we can specify the entire action of a unitary gate or a logic gate quantum mechanically by just acting on our basis vectors, which are these 2. If you have a multi-qubit gate, which is acting on more than 1 qubit at once, you have to write out all of those basis vectors, and they do scale. So for 2 qubits, your basis vectors, for instance, are like this, writing them in binary order, like so. Okay. But for a single qubit gate, 0 and 1 suffices. And then you can specify the action on any arbitrary state by combining these 2, essentially. So if I have some arbitrary state given by alpha 0 plus beta 1, the NOT gate will essentially switch those 2 amplitudes, which you can kind of quickly check for yourself makes sense. All right, when you're using linear algebra, you can use this to determine what your gate should look like. So here's my little placeholder matrix, and I know if I act on it, if I use it to act on my 0 state, I should get out my 1 state, and I know how to write those. That tells me 2 of my elements here. And then if I do the same thing, acting on the 1 state, knowing I should get out the 0, that tells me my other 2 elements, and then I can perfectly specify my polyhex gate, my NOT gate. And generally speaking, this always works. So if you know the action that you want from gate, and you don't necessarily know exactly what it looks like, then you can use linear algebra to solve for all of your elements. Okay. Now, classically, you have only the 1 single bit gate, but quantum mechanically, you have infinitely many, because any unitary matrix can be written as a quantum gate in theory. In practice, there's a certain set of native gates for a system. So depending on who's building the quantum computer, there are some things that they know how to build easily. And these are the native gates of the system. Normally, these are universal gate sets, which means that you can take any other unitary gate and break it into pieces that are completely composed of these universal gates, these native gates. In classical computation, there's only one universal gate set. And I forget what the gates are. Feel free to mention it if you know, but in quantum computing, there are multiple choices. You can just use whatever one makes you happier. You have to have a CNOT, which is a controlled NOT gate, but other than that, you know, there's a lot of freedom. So a common choice is the CNOT, Hadamard, and T gates, with T being like a phase shift, a relative phase shift, and the Hadamard is a superposition creating gate. May I see? Yes. Sorry, dog. Another common choice is CNOT and the polygates. The polygates can be viewed as like rotations on your block sphere. Okay. All of them actually can be mentioned as rotations of your state vector on your block sphere, which is what was trying to be visualized here. For instance, you might have a Hadamard gate. So this is how you write the Hadamard in linear algebraic terms, but the essential action of it is to take your 0 or your 1 state and put it into a superposition. So this is the action it has on our 2 basis states for a single qubit. And we call these the plus and minus state respectively, based on what operation's going on here in between the 2 qubits, but they're equally weighted superposition. And the way you can look at this is first a rotation here about the y-axis, and then another rotation here about this plane, and this will put you up from, it'll take you from your plus state to your 0 state. And then you can also view this going backwards. A Hadamard on your 0 state will take you to your plus state. And that's because Hadamard has this fun property where a Hadamard square is equal to the identity. And you can check that if you feel like it. So yeah, you can take any arbitrary unitary and put it on a quantum computer by breaking it down into these universal gate sets, all of which can be pictured as rotations on the block sphere. And you can also specify any unitary using these rotations, using a combination of a phase shift, a relative phase shift, and the rotations of the block sphere. What does that look like? It looks like this decomposing single qubit operations box, where this might look like they just pulled it out of nowhere. This is a result from a paper called Elementary Gates for Quantum Computing, which is like one of my favorite references whenever I'm doing quantum computing. It's Branco et al. It's published in 1995, and I personally guarantee you that Roy and Elisa have this paper because I use it on literally every project, and I've sent it to everyone. But so this basically gives you a recipe for breaking down single qubit gates in terms of your rotations. Okay, so that's single qubit gates. What about multi-qubit gates? Well, the most typical multi-qubit gate is the 2-qubit controlled NOT gate. It is referred to as the C-NOT gate. The way it acts is you have two qubits. One of them is a control qubit. When we write out our circuits, it looks like this. So your dot is a control, and it basically does nothing to that qubit. And then your target looks like a little target, and it flips the bit, if and only if your control is in the left state. Okay, so if you look at the truth table, these are your 4 basis states here. So 0, 0, 0, 1, 1, 0, 1, 1. And you can see that the action of the C-NOT is flip the second bit if only the first bit is 1. And this is your outcome there. And then you can describe the action on a superposition state as well by combining these. And you'll get something that looks like this guy. Okay. Another way you can do it, if you don't like truth tables, is you can describe the action using this sort of bitwise addition notation, which can be really convenient for very complicated quantum circuits. Just because when you get to higher numbers of qubits, your basis states start to really add up. Like your dimensionality goes as 2 to the n. So truth tables can very quickly get unfeasible because you'll have a whole sheet of paper of just truth tables, and then looking back at it, it might not be apparent what the action of the unitary is doing. So sometimes we like to break it down using these sort of binary operations inside of the ket. So in this case, this little symbol here, the target symbol, is bitwise addition, or addition modulo 2. And so modulo 2 just means divided by 2 afterwards. So you can double check, coming up to your truth table. 0 plus 0 is 0, that works out. 0 plus 1 is 1. Same thing here, 1 plus 0 is 1. And then 1 plus 1 is 2, modulo 2 is 0. So completely equivalent. And that might just make your life a little bit easier. You might recognize this if you know your classical gates really well. This is very similar to a classical XOR gate, which is the only multi-bit classical gate that we can repurpose to work in quantum physics. And this is the only one we can use because this is the only one that can be easily made reversible, like your NAND and whatever. They don't act reversibly. The truth table is bent. Well, that doesn't change the truth. It's still true. Okay, so this is the only classical gate we can use for our purposes, but luckily we can use it to create all of our other multi-qubit gates. And again, you can have infinitely many multi-qubit gates because you can have infinitely many single unitaries, and then you can always create multi-qubit gates by combining C-NOTs and single unitaries to create controlled unitaries and other such things. And this is how you could write a controlled unitary. Like so. So an example here, which I didn't read far enough into the text to realize they also give until after I'd drawn it out, is the swap gate. So swap does exactly what it says on the 10, takes your 2 qubits, takes some swap places. And you can make it out of 3 C-NOT gates. And so if you want to do the calculation long form, it looks like that. So it looks like this. So you start with, this is your initial state. You do the first C-NOT where it's controlled off the second qubit to get this, and then the third on this guy, and then the second on this guy, and then finally you'll arrive here, and you can check it with the initial to see that all of your qubits have been swapped for each of your basis states. So checks out. You can also use your binary addition to see this. And so maybe if you need some practice with binary addition, feel free to go through, do that, and you already know what the answer should be. So it should be a quick check that you're understanding how it's working. All right. Now back to measurements. I mentioned before you can measure in a basis other than your computational basis, which you might want to do for protocols like teleportation. So the other most common basis other than your computational basis is your plus minus. And those are created using the Hadamard gate. So Hadamard on 0 gives you plus, which is defined to be this superposition state where you're adding your 0 and 1 together. And then Hadamard on 1 gives you minus, where you get this minus sign here. And you can check very quickly that this basis is orthonormal. So if you take the inner product of plus with plus, you'll get back 1. Same thing with minus and minus. But if you take the inner product mismatched, you'll get 0. So that's convenient. Then you might say, okay, well, what if I have a state 0 and I measure in the plus minus basis, what's my probability to get that? And you can quickly see just by examining that your 0 state is the plus superposition of your plus and minus. So you have 50% chance of getting plus or minus out of that. And similarly with your 1 state. Notice that the magnitude here doesn't matter in your probabilities because you always take magnitude squared to determine your probabilities. Okay, so finally, you can write our typical, we can use this action on our basis states to write our typical unknown qubit, the manner that I have been before, rewrite it in terms of plus and minus, and then when you simplify, you'll see that your magnitudes are now plus your previous amplitudes or minus your previous amplitudes, like in between. So that's a cute little fact. But in general, you might have some other bases that you're measuring, might not be orthonormal, so it's always good to check. And this is the same general prescription you can go through to see how they act. In a circuit, there's a couple different ways people might indicate a measurement. You might see a little dial, sometimes with an arrow, sometimes with just a line. And they might write Z. If they write Z, that just means the computational basis. Or you might see this guy, which is just a detector. It's just detecting things. All of these in a circuit indicate measurement. Sometimes there's an outcome from the measurement. Oh, no. Okay. And if you're sending something from measurement, once you measure, it's classical. So the output might look like that. And that just means a classical bit is being transmitted. All right. Other circuit details to note, particularly if you're more used to classical circuits than quantum circuits, is you do not allow feedback loops. Everything has to go straight through. It's linear. No irreversible operations, which means no fan-ins where they all come to a point, and no fan-outs where they spread out. So the second one leads to the question posed by section 1.3.5, which is state copying circuits. And that still counts as a question. So Betteridge's law of headlines applies, which says that any headline that ends in a question mark can be answered by the word no. So can you copy an unknown state? It's actually very fundamental that you cannot. So you can, a lot of people run through by like proffering a way that you might be able to copy some state. But it's actually really simple to prove that you can't. This is my thrown together version of the proof. So assume that you can, and that you have these two unknown states, psi and phi, and you have some unitary circuit here that copies them onto some other state. The state that this guy starts in literally doesn't matter. Okay, so we can write our two unknown qubits this way, and then we can act on them with U, such that you acting on the first one gives you this guy, and you acting on the second one gives you that guy, right? All fine and good. And then we can consider the inner product. So remember what I said before about unitaries preserving the inner product. What that essentially means, okay, so I said it like it must preserve probability. So this must equal 1 in order for us to get our normalization condition. And what unitaries preserving probability or preserving the inner product means that if you slam the identity in here, which is U dagger U, like so, this must also equal 1. which makes sense because this guy is equal to the identity, right? So this is not allowed to change the value of your inner product. That's the important note that we're going through here. So we take the initial inner product between our two unknown states, and we get this guy. And again, just this is always true for any ket. And then you can consider acting on each of these with you. When you go to take the inner product, you take the dagger of everything. So that means you reverse the order. If it's a ket, you flip it to a bra. If it's a bra, you flip it to a ket, and you add a dagger to any unitaries before. So that means the inner product after applying the unitary to these two states looks like this, but this guy should just be an identity. So this should be equivalent to what we had before, but if instead we use it to act on the states, we get this guy, and we do a bunch of algebra, and at the end of the algebra, we get this guy, which is equal to the inner product you got before squared, which in general is not the same thing. It is in fact only the same thing if it's equal to 0 or 1. So if your initial states you were considering were perfectly orthogonal or identical, perfectly overlapped. Since this is not in general true, this unitary doesn't preserve the inner product. Okay, our inner product has changed between before we had it and after we introduced it, which means it's not a unitary. And if it's not a unitary, you can't use it in a quantum circuit. Therefore, there is no quantum circuit that acts this way. QED, epsilon less than 0. This fancy thing, which is called the no cloning theorem, which is a very interesting name, I think, is actually very fundamental if you don't let people mad at you for breaking causality. So if we have someone going over teleportation after me, a lot of people are saying, no, you're transmitting information faster than the speed of light. You're actually not allowed to do that because of the no cloning theorem. If you don't have the no cloning theorem, people, Einstein fans, would be a lot more mad at us than they already are. Okay. So that was the no cloning theorem, and then finally we're going to end on the Bell states. So the Bell states, or the EPR pairs, are maximally entangled states, which I kind of mentioned before that they were entangled. Maximally entangled basically means it doesn't matter what basis you write these guys in, they're always going to be entangled. You absolutely cannot separate these even a little bit. And this is the one that was introduced before. And the book writes them something like ket beta, and then this is 0, 0, and this corresponds to the input you put in. But in most literature, they're going to not be written that way. They're going to be written with these psi and phi pluses, capital plus minus, something like that. This is just how they're written in literature. Why do we care about Bell states? Well, for all of the reasons I mentioned before, where they're entangled, they piss off Einstein, all of those lovely features. And then they're super useful for pretty much any quantum algorithm that you might want to do. And moreover, we can use them for an example quantum circuit because they're created from the Bell state circuit. So this is the Bell state circuit. It's a simple 2-qubit circuit. And using these two gates, the Hadamard and C0, you can create all 4 of your Bell states just by putting in different inputs. And you can check this pretty easily by using the definitions of the Hadamard and C0 we used before, that your 0, 0 gives you phi plus, and then 0, 1 gives you psi plus, and so on and so forth. All right, I don't know why, that's where they chose to end the section, but that is it. Those are all of my notes. I apologize for the poor handwriting, and yeah, hope that was useful.
All right. So, any questions? I have Lisa.
So Elisa says, I think there was a whole paper that spoke about time travel written by a scientist. He didn't know you couldn't clone quantum states. And then people debunked that by discovering the no cloning theorem, but I cannot remember his name. That's interesting. Yeah, I didn't know about that. I know Mark Wilde had a time travel paper, but he knows you can't clone quantum states. So
Okay, I have a question.
oh great.
Okay, so I kind of remember a result from classical computing that something like if you were to use instead of bits some 3-level information, that there's no advantage to doing that. Is that also true in quantum computing?
Okay, so that's the discussion of the qubit versus the qubit.
Yeah.
And so yeah, a qubit is a so physically, if you're doing a qubit, you might have a system that's like an atom that is excited or not, or a photon that is there or not. That's your qubit. Versus a qubit, you might consider an atom with more than one excited levels. Qubit, as Roy just pointed out, is the generalization of this concept.
Yeah.
So qubit is 2, qubit is 3, qubit is however many you want. So you might have more than one excitation levels. That's like a discrete example. But you might also have, I would go back to optics. So in optics, you might have something like LG modes, which is infinite. Yeah, and Roy points out you can use orbital angular momentum. And this essentially gives you a bigger base to work off of. And I believe that there is an advantage to doing these continuous quantum computing style algorithms, and just that certain problems I think are easier with them. But caveat to this is that so when you talk about quantum computers, you have 2 types of quantum computers, universal and non-universal. And for everyone who's interested in the prospect of quantum computing, we care about universal quantum computers, which are, they can solve all of the problems any other quantum computer can solve, versus non-universal solves only their problem. And there are many different ways people are trying to build universal quantum computers, be it trapped ions or photonics or superconducting qubits. And there's a paper, I don't remember the name or the authors, that actually demonstrates that these are all equivalent. So maybe you're doing your optical setup with your qubits that are, you know, in principle infinitely dimensional. But yeah, I guess you don't get an advantage for that in the long term in terms of computational complexity, because you can do everything you do on these high-level optical setups on your discrete qubit setups. They're both universal and they're equivalent.
Maybe there's a proof of this similar to how you would do it in classical computation, like Boolean algebras or whatever. But yeah, go ahead.
Okay, so Alex said, I have a tangential question. So if the Hilbert space is so much bigger than classical bits, what does that mean for NP computation as opposed to classical? Since I know you talked about reasonable computational time with the extended Church-Turing thesis. Okay, that is a fantastic question, and that is the crux of the debate between your quantum computer proponents and your classical computer, like that sort of adversarial relationship. So I'll start off by saying NP hard, NP complete problems, which are problems. Okay, so first backing up a little bit, if you don't know what I'm talking about with NP computation, that means non-deterministic polynomial time. So for computational problems, it's often useful to talk about their complexity, which is how hard it is to do the problem. What sort of resources do you need to do them? And classical computers can do anything in P complexity, which is polynomial time. They can do that efficiently, but they cannot do NP, which is non-deterministic polynomial efficiently. Non-deterministic has to do with like you introduce some probabilistic aspect to your computation, and then you can do it efficiently. So when I say NP hard or NP complete, that refers to a class of problems which are all like equivalent to each other. They map to each other in polynomial time. And they solve all of the problems in NP complexity class. However, there's like an in-between level of problems that are in NP, but not NP complete. Okay, so that's like in between your P complexity and your NP complexity. All right, that context being established. What does the Hilbert space mean for NP computation? Well, classical computers can't do it efficiently, or at least we don't believe so, because that means if they could, then NP is equal to P, and that's fun for other reasons, but we don't think that's true. And we believe that this higher dimensional Hilbert space, plus some other stuff, some other fun quantum mechanics things like entanglement, and your relative phase shift and your superpositions, they give you some more computational power, so you actually can solve some of those NP problems. We don't think you can solve the NP complete ones. Of course, we'd be very happy to be wrong about that, and there's no proof that we can't, but we know that we can solve some NP problems that classical computers have not been able to solve. So the go-to example for that is Shor's algorithm. So all of RSA encryption, which is like the most popular form of encryption, is based on the factoring problem, which is that it's really hard to factor really big numbers. And classically, it's not efficient, it's NP. But quantum mechanically, we already have an algorithm that can do it efficiently. So that's Shor's algorithm. So just with this one algorithm, we've shown that we get a speed up, we get a little bit more computational power.
I think the speed up from Shor's algorithm as opposed to the fastest classical is like exponential.
Yes,
Yeah.
As opposed to like Grover's search algorithm is only square root, which is nice, but it's not amazing. But yeah, exponential speed up from Shor's algorithm. And so in general, when they look for, sometimes people bandy about the terms quantum supremacy, they're looking for some sort of exponential improvement, be it time or even space resources. So like you might need exponentially fewer bits. And that's an advantage from using a quantum computer too. So that was a very long answer to your question, but the question's really at the heart of why quantum computing instead of just classical computing. So.
All right. I think we gave Marguerite way too much to talk about today.
Yeah, that took a while. My voice is like going out.
Let me stop the recording before we move on here.